So here we know that to find the tension in the cable, we know that the sum of torque is going to be equal to 0. The system is in rotational equilibrium. So we can say that the torque due to the cable is going to be equal to the torque of gravity. So we can say that the tension times the length of the tension force, or rather the tension times the length from the tension force to the rotational axis is going to be equal to the weight times the uh, length between the center of mass and the axis of rotation. So we can say, we also know that the length of the center of mass is going to be equal to the full length times cosine theta divided by 2, or L over 2 times cosine of theta. We also know that L sub t is going to be equal to d sine of theta. So we can say that t d sine of theta is going to be equal to the weight times L cosine theta divided by 2. So we can say that t is going to be equal to the weight times L times cosine of theta divided by 2d sine of theta. And this is going to be equal to the weight times the length divided by 2d tangent of theta. So we can say that this is going to be equal to 47,000 newtons, the weight, times the full length, so 14.0 meters, divided by 2 times 3.5 meters, times tangent of 37 degrees, and we find that the tension in the cable is going to be equal to 1.2 times 10 to the 5th newtons. Again, the tension in the cable. So this would be your answer for part A. And then for part B, they want us to find the reaction forces. So f of x will simply be equal to t, and this would be 1.2 times 10 to the 5th newtons. And then sum of forces in the y equals 0. The y component of the reaction force would be just simply equal to the weight, so 47,000 newtons. And we find that the angle of the reaction force is going to be tangent -1, 47,000 divided by 1.2 times 10 to the 5th. And this is equaling 21 degrees above positive x-axis. Let's clean this up. Positive x-axis. And then for part C, we know that the cable breaks, so they want us to find the angular acceleration. So if the cable breaks, we can say that the sum of the torque is going to be equal to the moment of inertia times the angular acceleration, and this is going to be equal to WL cosine of theta over 2. So we can say that ML squared times alpha divided by 3, ML squared divided by 3, that's the moment of inertia about a rod rotating about one end. And so this is going to simply be equal to mg L cosine of theta divided by 2. And let's solve for alpha. So the m's cancel out, and the angular acceleration is equaling 3g cosine of theta divided by 2 times the length. And we can solve and say that angular acceleration is going to be equal to 3 times 9.8 times cosine of 37 degrees divided by 2 times 14 meters. And this is giving us 0.84 radians per second. So this would be the angular acceleration after the cable breaks. And then for part D, they want us to find the angular velocity. So For part D, we can simply say that the gravitational potential energy is going to be equal to the rotational kinetic energy. So this would be mass times gravity times the height of the center of mass will equal 1/2 times the moment of inertia of a rod times omega squared. And we know that YCM is going to be equal to L sine of theta divided by 2. So we can say that mg L sine of theta divided by 2 is going to be equal to mL squared omega squared divided by 6. And so omega is going to be equal to 3g sine of theta over L to the 1/2 power. So omega is going to be equal to 3 times 9.8 times sine of 37 degrees divided by 14 meters, all to the 1/2 power. And we find that the angular velocity is going to be equal to 1.12 radians per second. So this would be your answer for part D. We simply need to use the conservation of energy in order to find the angular velocity. That is the end of the solution. Thank you for watching.